In 1877, Charles Friedel, who is the fine fellow shown here, and James Kraft, shown here, reported that alkylation can take place when benzene is treated with an alkyl chloride in the presence of aluminum chloride. Now, aluminum chloride, as shown here, is a strong Lewis acid base. It's also shown there as well. This is called a Friedel-Crafts alkylation. And basically, I want to remind you that an alkyl group is just a bunch of carbons. And so if you can take a bunch of carbons shown here attached to a chlorine with aluminum chloride, it will undergo an electrophilic substitution reaction. And you can add the group here, basically in red, the chlorine is replaced by the benzene. Okay. Now, so let's look at this mechanism first. And so when we look at this mechanism, we're going to draw the aluminum chloride. So here, and then we are going to draw the alkyl chloride here. Okay. Now, the aluminum chloride, like I mentioned, is a strong Lewis acid catalyst. So these chlorine, those are the nucleophile, and it's going to come in here and attack that aluminum like an electrophile through a coordination reaction. Now, through this coordination reaction, what you're going to see is this group form. Okay, and then it's going to undergo heterolysis, right, where these electrons go here. Now, once it does that, it's going to form, and that's heterolysis. Let me write that down. Cl3 AlCl here, and it's going to form a carbocation here. Now, remember, we're forming a carbocation, so you need to watch out for carbocation rearrangements. Now, we have an electrophilic addition reaction is next, just like what we've seen before, where we have the benzene ring here. And what happens is that these electrons are going to come down and attack that positive carbocation there. When that happens, right, what you're going to see here is this intermediate, and then this will go through an electrophilic elimination. Where these electrons will come here. They'll grab that proton, and then these electrons will go there to reestablish the aromaticity. And then you have added that alkyl group on to the benzene, just like that. So, there can be other alkylations that occur. So Friedel-Crafts alkylation reactions take place in the presence of other Lewis acid catalysts like FeCl3 and FeBr3. So watch for that, as well as aluminum chloride. So we can also see these catalysts being FeCl3 and FeBr3. But they can also take place under other conditions that generate carbocation intermediates, two examples of which are shown here. In the acidic conditions, basically you convert the OH group into an excellent leaving group, which departs as water. Okay, so basically this gets protonated, and anytime water forms, of course, it's an excellent leaving group. This is a tertiary carbocation, so it tends to be more stable, and so you can add here. And then in this equation here, what you're going to see is the protonation of a double bond through the acid here, and that's going to produce a carbocation intermediate directly. And this is the same step that makes up the beginning of an SN1 or an E1 and electrophilic addition reactions, right? And so we get a carbocation, and then it can also add to a benzene. Cyclohexylbenzene, which is shown here, has long been studied as an overcharge protection agent for lithium-ion batteries, and it helps extend the life of those batteries. So there's a reason that we want to synthesize this. So let's look at a problem. So this problem sets us up, and it says, show how to synthesize the following compound in a single reaction using benzene as one reagent and an alkyl halide as a reagent, an alkene or an alcohol as the other reagent. So when we go through and do this, here's some things to think about, right? Which bond must be formed in the target? And so when I look at this, I say, okay, hey, look, I got 6 carbons here, and here I've got 6 carbons, that's 12, 13, 14. So I've got to form some carbon-carbon bonds, right? And it's probably there's going to be probably some sort of connection mechanism between these two here. So when we look at this, how would we undo it? Okay. And so when I think about how I would undo it, I'm thinking we'd probably undo it there. Okay. Because when we think about what electrophile would be necessary as a precursor, if we undid that there, and we were undoing this, we're basically undoing an electrophilic aromatic substitution reaction where we would have benzene, as mentioned, plus this electrophile here. And I can see that fairly clearly when I look at kind of where I'm cutting in my line there. Then basically we say, how could that electrophile be produced from an alkyl halide, an alkene, or an alcohol? And so as we look through this, we say, okay, hey, look, let's do the first one. Let's do A. Where that positive charge is, I would put a chlorine, right? And use aluminum chloride, and that would get me that intermediate there, which could then go on and react with benzene to form our product. Now I'll put that in brackets because I just want to simplify kind of how I show it. You'll see why in a second. Right there. Okay, then for the next one, it's saying, look, what about an alkene? Well, if I do an alkene, if the structure looks like this, right, and I use an acid, H2SO4, then I would get that intermediate. So that's B. And then C, right? We have H2SO4, and then that would give us that intermediate. So very versatile, lots of different ways that you can go through and do this. Now, there are some limits to this reaction, okay? And so let's look and talk about those. In the Friedel-Crafts alkylation, you might expect the product of this reaction here, you might expect this to be produced, right? Based on what we just saw, where we've got the chlorine here, there should be a positive charge, and that would come on and be produced. But we have a carbocation rearrangement, and with the carbocation rearrangement, we rearrange where that carbocation is right here because it's stabilized by resonance stability, okay? Because it's right here next to this group. So this is the major product. So Friedel-Crafts alkylations, anytime we form a carbocation, we've got to watch for carbocation rearrangements. So these are susceptible to carbocation rearrangements, which is a great thing if you are trying to make this. It is not a good thing if you're trying to make this. So not all carbocation rearrangements are bad per se. It just depends on what you're trying to make. Now, let's look at the partial mechanism here because I just want to remind you about this. What we see basically is we get a hydride shift and then it undergoes the electrophilic addition and electrophilic elimination, and that's how we see this product being made. So just a kind of brief reminder here. Now, this particular equation here shows another example of a rearrangement in a Friedel-Crafts alkylation. So look, when you undergo the coordination here, and then what you see is a what we would expect is a primary carbocation to be formed, but we know those aren't very stable. And so what happens is heterolysis and the hydride shift occur together. So the hydride shifts here, and then you get heterolysis, and you get a secondary carbocation, which is a lot more stable than the primary carbocation. So primary, if you've got a situation where you're going to have a primary carbocation, in this situation, it's going to go through a rearrangement to give you a secondary carbocation rearrangement, a secondary carbocation. So we really have to watch for carbocation rearrangements. In addition to kind of this issue, in some cases, no Friedel-Crafts reactions will take place at all. So what we see here, right, is you have another benzene ring with a Cl, right? So this is like a benzyl chloride or a vinyl chloride here. And so the sp2 hybridization of a carbon increases the strength of the carbon chloride bond. So basically, if you've got a chlorine next to a double bond, that increases the strength of this bond, and it decreases the stability of the carbocation that would be produced. So that's not going to react at all, right? So in general, a Friedel-Crafts alkylation reaction does not occur unless the halogen of the alkyl halide is bonded to an sp3 carbon. So, right, the halogen needs to be bonded to an sp3 carbon, right? And so that's one of the limitations of this reaction. And then the third limitation of Friedel-Crafts alkylations arises because each alkyl group attached to an aromatic ring makes the ring even more reactive towards electrophilic aromatic substitution. And so this can result in a mixture of products. And so Friedel-Crafts alkylations can also result in polyalkylation. So there are some pretty significant drawbacks to using the Friedel-Crafts alkylation in a synthesis.